In this video, I'm going to discuss the alternating series estimation theorem. Estimating a sum. What we can do, we can compute a partial sum of the convergent series, and in this case, it must be the alternating series. And we can use this partial sum to approximate the entire sum, the total sum S. However, this approximation is not going to be really helpful unless we will find the accuracy of the approximation. That means what we will have, the error involved in using the approximation that the partial sum S sub n is almost the same like the entire sum. Of course, we will have a difference and we will call this remainder. And let's see on my on the expanded form. That means what we do have an alternating series, of course convergent, because otherwise it's not even logically to talk about the sum if it's divergent. That means this is convergent, and this is the expanded form. Of course, we adding every other term is negative. And I do have a few lines. The first line represents the partial sum. That means I am just ending at the term b sub n, and this is my s sub n. My longer line underneath represents the entire sum. And we can see the small difference. That means this difference. My line is a little bit slopey. This difference, of course, is the long line minus the shorter one, which is the entire sum minus the partial sum. And this will be our remainder, or we can say error. Okay? And magnitude. We have to estimate the accuracy of this error. How big, or, of course, how small is this error? That means let's look and let's try to estimate. One more time, the error will be defined as the entire sum minus partial sum. We know that. Okay. The partial sum I expanded. That means S sub n means all of the terms adding up to b sub n. This represents the entire sum, S. And I have expanded form one more time. That means this is the entire sum S, and this is just up to b sub n, which is the partial sum, adding n terms. And let's see what's happened. Having this, the difference between the S, the entire sum, and the partial sum, we can nicely see that most of the terms are cancelled out. Like we were looking in the previous slide on these lines, the big line minus the shorter line. That means we definitely have the terms up to b sub n, it's cancelled out. That means what's left? Always we will left with the next term that is not including, okay, the next term, which is b sub n plus 1, and we still subtracting, adding, and subtracting. All of the terms are getting smaller and smaller. This quantity will be always positive anyway, but I still keep the absolute value. However, we can see that the remainder, which is the error, it's equal to this b sub n plus 1 minus the other terms. However, subtracting more terms, I am making even smaller my error. That means my error is less than, definitely less than the next missing term. That means this is really nice property. Okay? And I can say that the size of the error is smaller than the next term, which is b sub n plus 1, or I can say that the magnitude of the error is going to be no more than the magnitude of the first term that are not including in our partial sum, which means adding n terms, the next term that is not including is the term n plus, b sub n plus 1. And that means the first neglected term. Okay, that means this is the alternating series estimation theorem. Let's have the summary. if the infinite series, the alternating series, okay, defined as a summation from 1 to infinity, -1 to the n minus 1, and the b sub n is the sum of alternating series that satisfies all of this condition. We recognize this. B sub n is positive, limit at infinity of b sub n is 0, and of course b sub n is decreasing. That means we are satisfying all of this. This means that the alternating series is convergent. Then, approximating a sum by the partial sum, we have the size of the error of the remainder. The size of the error, s minus s sub n, is always less than the term b sub n plus 1. And we know what this means. I do have the proof of this. You're more than welcome to pause the video and go through. And also this illustration, this is also showing me that the difference between the particular partial sum and the actual sum, it's always less than the next term. And we can even pick one value. Let's even say this is the value of the entire sum, and this is value of the 5 terms, s sub 5. That means that's the difference between them. And we can see my line is definitely less than the next term, which means this was s sub 5. This will be the magnitude of the next missing term, which is b sub 6. And we can see the top line is longer than this, than the bottom one. The bottom one is the difference. The bottom one is the difference between the entire sum and the partial sum. And this is definitely less than b sub 6. Of course, the magnitude. And as we can see, that's a nice proof too. Okay, let's practice and let's solve a few examples. Exercise number 1. What minimum number of terms of the series, the summation from 1 to infinity, -1 to the n over 10 to the power of n factorial, do we need to add in order to find the sum with the error less than 0.000005? Okay, that means what we know. We know that the error, the remainder, is less than the next term. Okay? That means we still don't know what is the minimum number of terms. Minimum number of terms. That means what we will do. We have to find out a term, okay? And I want this error, I can write, to be less than 0, 1, 2, 3, 4, 5. 1, 2, 4, 5. And actually, I will change this number because this is not telling me much and we don't have a calculator to support ourselves. That means we will do a little bit trick. I will rewrite this as a fraction. That means this is 5 divided by 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6. And I can simplify. 10 divided by 5 is 2. That means my size of the error must be less than 1 over, and I have 200,000. I believe that's correct. Okay, that's me now. What I'm looking for, I am looking for the term that is less than 200,000. And the only thing that is I have to do, I have to find a term that corresponds to my inequality. Okay, let's see. Looking at this alternating series, I can see that b sub n is just 1 over 10 to the power of n times n factorial. That's me now. Let's compute b sub 1. B sub 1, I will just substitute 1 instead of n. N factorial is, 1 factorial is 1, 10 to the power of 1 is 10, 1 over 10. But 1 over 10 is much, much greater than the number that I am looking for. Okay? I want my value, my term, to be less than 1 over 20, 100,000. Okay, b sub 2 will be 1 over 200. I hope we can see this, because 10 to the power of 2 is 100, and 2 factorial is 2. 2 times 100 is 200, but this is still greater than 1 over 200,000. Okay, let's find b sub 3. b sub 3 is 1 over 6,000, because 3 factorial is 6, and 10 to the power of 3 is just 1 and 3 zeros, 1,000. 1,000 times 6, of course, is 6,000. I believe this is still greater, because what I'm looking for the denominator to be greater than 200,000, then the whole fraction is smaller. Okay, let's check b sub 4. b sub 4 will be 10 to the power of 4, which will be 10,000, and 4 factorial is 24. That means 24 and 4 zeros. That's what I write. It's 24,100,000, and I see that 240, let's just look at this 240,000 is definitely more than 200. That means if the denominator is bigger, the whole fraction is smaller. Okay, that means what I did. I found a first term, the minimum number. I found the first term that is less than my desired error. Okay, that means we can see b sub 4 satisfies my inequality. Okay, b sub 4. But now I have to be really careful, because 4 is this quantity. Right? 4 is this quantity. That means if I have to recover n will be one number less, because we can see b sub 4 was the first term that was not including in the sum. That means I have to take the partial sum just including 3 terms. Okay? Always one number less. Since the fourth term is less than the desired error, we need to add the first 3 terms to get the sum of the desired accuracy. Okay? That means the final answer is, I can even write n equals to 3, because that's the minimum. However, all of the other numbers greater than 3 will also satisfy the equation. But the question asks for the minimum numbers. Because when I add more terms, automatically my error is even smaller. That means I'm definitely satisfying the condition of this question. Okay, but the minimum number is 3. N equals to 3. Okay, let's do the same question, just different condition. Find minimum number of terms of the series, alternating one, of course, -1 to the n over n times 5 to the n. Do we need to add in order to find the sum with the error less than 1 over, I think it's 0.0001, but what we will do, the same what we did in the previous question, we do have 10,000. I believe 1, 2, 3, 4, 4 zeros, 10,000. That means the error must be less than 1 over 10,000. Because my b sub n, I can possibly write here, it's 1 over n times 5 to the n, and we can definitely see it's positive, decreasing, and limit is 0. That means this is infinite, the alternating series convergent, which it's actually makes sense to talk about the sum. Okay, that means the same thing. That's my alternating series estimation theorem. I'm looking for the term that is less than or equal 1 over 10,000. And again, finding the term, I always have to take one number less for the partial sum in order to keep this accuracy. Okay, let's do the same. B sub 1 is 1 over 5. Let's see if we agree. 1 n and 5 to the power of 1 is simply 5. Okay. This is definitely greater than 10,000 in the denominator. B sub 2 is 2 times 25. 2 times 25, of course, is 50. The same. This is definitely greater than my small fraction, 1 over 10,000. B sub 3 will be 3, and 5 to the power of 3 is 125. I think this is still, if I multiply 3 times 125, I'm not gonna get 10,000. This is still bigger. Okay, let's try 4. B sub 4 is 4, and 5 to the power of 4 is 25 times 25, 625, we all know that. And if I multiply 600 times 4, I'm not gonna get 10,000. That means this is still bigger. And let's say this one, B sub 5 will be 5, and 5 to the power of 5, we have to take 625 and multiply again by 5. I think we can take time somewhere on the side and get this. Okay, but now what I'm getting, multiplying the number around 3,000, I will get 15,000. That means this number will give me a fraction less than. That means, yes, I found that the term B sub 5 satisfies my inequality, my theorem. That means we have to remember 5 represents this number, n plus 5. Then the conclusion is, since the fifth term is less than desired error, we need to add the first 4 terms, because 4 plus 1 is giving me 5. That means n is 4, or, of course, we can pick any number greater than 4. Because if I add more terms, the partial sum is sub 4, but I can add 5 terms, I can get the partial sum with the 6 terms, 7 terms. I will be adding more terms, then I will be making error even smaller. That means I will be definitely in that, I will keep that accuracy. Okay? That means please note that any number equals to 4 or greater than 4 number of terms will keep this error less than 1 over 10,000. But what we're looking for? We're looking for the minimum value. 4 is the correct answer for this question. Okay, let's look at the next one. What minimum number of terms of the series -1 to the power of n over n factorial do we need to add in order to find the sum with the error less than 2 over 10,000? The same thing, let's simplify a little bit. 2 over 10,000, I can simplify 2, divide by 2 is 1, 10 divided by 2 is 5. That means I do have my error less than or equal 1 over 5,000. Okay, that means the same idea. Let's look at this is my alternating series. The formula for B sub n is just 1 over n factorial. Positive, decreasing, limit 0, it's definitely convergent. The sum exists. That means this makes sense to even talk about this question, this accuracy. Okay, let's look at the term that has a value less than 1 over 5,000. Let me write my B sub n, maybe over there. Okay, B sub 1 is just 1. Of course, much, much bigger than 1 over 5,000. B sub 2 is 1 over 2 factorial. Okay, and 1 over 2 factorial. It's 1 over 2. Let me, 1 second, I'm just trying. Okay, that means this is 1/2. Of course, it's much bigger than 1/5,000. Okay, let's keep working. 3 factorial, I think it's 1 times 2 times 3, it's 1/6. This is also bigger than 5,000 in the denominator. Let's keep working. Probably 4 is 1 times 2 times 3 times 4 is 24. That means 24 is also not giving me a fraction smaller than 1/5,000. 5 factorial is 24 times 5, which will be 120. And this is also not good. Okay, I think we can see, but let's see. 6 factorial, we have to multiply 120 times 6, and we will get 7. We will get 720, which is also greater than this fraction. B sub 7, 7 factorial is quite big number, but what we can do, we have to multiply 6 factorial times another number, 7. 720 times 7 will give me a number. I did the math before, 5,040. Oh, okay. That means this works. That means actually I don't know if my numbers are correct. That's the reason that is a little bit. We will correct it. This is 5,040. That means my denominator is greater. The whole. Excellent. That means actually not the 8th term, the 7th term works. Let me do the same notation that I did for the previous. 7 represents this number. That means I can change this. The 7th term is less than the desired error. Then we need to add actually 1 term less. We just learned this. That means if the B sub 7 works, we will add the partial sum of the 6 terms. That means the minimum number is 6. We also know that any numbers greater than 6 also works, because adding more terms, we're minimizing the error, but the minimum number is 6. Okay, that means this is still not big computation. Even if it's the exam type question and we don't have a calculator, we can still manage. Yeah? It is a little bit, required a little bit of arithmetic, but it's not a problem. Okay, that means 6 is the correct answer. Okay, and I have one more example. Okay, now the series below is convergent. Right? That means this is, and we can see is the alternating. The series below converges. Okay, I'm sorry, I'm just trying to correct my own writing. The series below converges, and that's the series. The summation from 1 to infinity, -1 to the n squared plus 10. Okay? And we can see the formula for b sub n is just 1 over n squared plus 10. Positive, limit 0 at infinity and decreasing. That means it is convergent. If we would like to estimate the sum, the whole sum S of this series by the sum of the first 7 terms. Okay? That means we just need to add 7 terms. Then the alternating series estimation theorem guarantees that the error is less than or equal, and we have to find a number. And we have to find a number. That's, let's see, that's the property again, that's the theorem. And what we're doing, we actually trying to find the error, estimate the error, adding 7 terms only. Okay? That means adding 7 terms, having a partial sum as sub 7, we will of course subtract from the entire sum, and this will be the error. And we know that again, the magnitude of the error is less than the magnitude of the first term that is not including, which will be 8. Okay? That means the error is definitely less than or equal b sub 8. And it's just enough to compute b sub 8 term. That means b sub 8 will be 8 squared plus 10. And we don't have to do anything, which is 64. B sub 8, of course, will be 8 squared, 64 plus 10, 1 over 74. That means the error is less than or equal 1 over 74. That's, I can put this number 1 over 74. Okay, and of course I just write the same thing because it's 7 terms, the 8, we don't have to write this. Okay, that's all of my examples. Okay. I do have a quick note for the estimation, for this estimation theorem. That means the rule that the error in this approximation is smaller than the first neglected term is like in general. And it's valid only for the alternating series that satisfies the conditions of the alternating series estimation theorem. Okay? The rules does not apply for any other types of the series. That means, please note, we can only apply this theorem for the alternating series. Thank you.